There's not a whole bunch that you have to do here, but there is some recognition. We can't use forces, well, I think we're going to have to assume that there might not be any friction here either. And I make that assumption lightly because in a few minutes we're going to change that assumption. But what the hallmarks of this being a conservation of energy question is that there is a clear change in height for one of the objects in the problem. And we know that the height of the object is related to how much gravitational potential energy it has. So I will remind you of something we talked about yesterday, that the change in potential energy plus the change in kinetic energy will equal either zero or the work done by an external force. It's one or the other. So if we're assuming there's no external force on the system, then this change ends up being equal to zero. And I'm pretty sure we saw through a little bit of algebra yesterday that this leads to the final state being equal to the initial state. Right? We did a little algebra yesterday to show that. Now, just take a look at your two states. We have a state here, which I will say is the final state, and a state here. What am I doing? That's not the final state. It's a state here that's the initial state, and a state here that's the final state. Right? The block starts at the top of the ramp and ends at the bottom of the ramp. If we choose those as our two states, the next thing we should probably figure out is what we're going to call our reference position. So I think this will make for a good reference level. I think it makes the most sense for the reference level. I mean, we can put the reference level anywhere we want, but if I put it here, then the block makes it to the reference level at the final state, suggesting that there is no gravitational potential energy at the final state. Now, in the old days, what I do is I just list all the forms of energy that could exist. You only have two. You list them at both states, and then just ask, is it likely that it has one or the other of these at each state? It can have both, but if it's not moving, it doesn't have kinetic. And if it's not above the reference level, it doesn't have potential. So in this problem, it looks like we start with potential energy and end with kinetic energy. Now, that suggests that we could write this as 1/2 mv squared for our final state, because there's no gravitational potential energy. And at our initial state, we have mgh. And there's no kinetic energy if it was started from rest. So then you just do the rest of the math here, right? Once you recognize this part, the physics part's largely done. You're just going to plug in numbers and come up with an answer. Can you do that part? And it's not a whole lot to do here. You're going to have, I notice the m's cancel out. So we'll just get v equals the square root of 2gh. So square root of 80, I think, so about 9. So let's just, 9 meters per second. Simple enough. Not particularly hard, right? So tuck that away in the back of your mind for just a minute and consider maybe a question that's a little bit harder, one in which maybe we don't get to make some assumptions about friction in this way. What if it makes it down here and the block only has a velocity of 4 meters per second? Now, if we had not just done this problem a minute ago, you may not know whether energy is being conserved or not. But normally, you might have a question associated with it that might give you a clue that energy is not conserved, like, can you tell me the work done by friction? Well, that would probably clue you in that there's an external force acting in your system, and therefore that external force is doing work. That changes this from a strict conservation of energy to a problem in which work is involved. Now, you should prove to yourself whether you actually are losing energy. We can do it real easy. We know that the amount of energy we have at the beginning, mgh, is going to be 2 times 10 times our height, which is 4. We started with 80 joules of energy. But at the bottom, the kinetic energy left over, 1/2 mv squared, Well, that's 1/2 times 2 times 4 squared. So we have 16 joules of energy. So it's clear that there was a loss of energy. So if we wanted to figure out how much work was done by friction, I think we just subtract these two numbers. But let's do it more strictly, right? Let's use this to figure out how much energy was lost. And if I do, remember this is going to be U final minus U initial. Well, the final potential energy is 0 because we're at the reference level, and the initial was 80. And then we're going to add the change in kinetic energy. Well, that's going to be K final minus K initial. Well, K final is 16 joules of energy, and the initial was 0. And this has to equal my work done. In this case, we know we're talking about the work done by friction. So it looks like negative 80 plus 16. So maybe negative 64 joules of energy was done by friction. Now, if this were a straight course, you could do more with this. You would know how far the block slid. So you could figure out the force of friction if you wanted. And from there, you could probably figure out the coefficient of friction. There's other ways this problem could develop. But strictly speaking, you have one or the other. You either are conserving energy or there's an external force that's adding or taking away energy. And this is what these two problems look like. This is a pretty pedestrian example. It's not got a whole lot of stuff. But I would like to take it up a little bit to maybe a more concrete example, a more useful one. So let's consider one of your homework questions, shall we? Or try to. All right, this looks like something in your homework? This thing? We've seen this before, right? Took it out a little while ago. One of the things that should be kind of in your mind is this idea that if I start the ball at the same height as the top of the loop, it should at least make it to that point, because it should get there right as the kinetic energy is going to 0. But we've done this before, and it doesn't make it back to the same height. Now, I don't want to trick you or something and say that there's friction or something. There's actually not a whole lot of friction here, but the marble's rolling. And one of the things you'll find out next semester is that there's more than one kind of kinetic energy. There's translational kinetic energy, which is change of position, but there's also rotational kinetic energy. So the marble has to split its energy between translational and rotational. So because of that, it's going to be traveling a little bit slower than we think it should be. But even so, if I just give it a little bit more potential energy, it still doesn't make it all the way to the top. And this isn't because there's not enough energy to get there. It's because in order for it to travel in a circular path, other conditions must be met. We already know that, correct? Net force equals MAC. And for it to travel in this particular circle, that V squared over R, that R means something there. And since the R can't change, if the V isn't great enough, then your problem is you're going to have a problem. So your unbalanced force, it's going to dictate whether you have a situation in which you can be in circular motion. And if the velocity isn't sufficient for the radius that you have, the ball will start tracing a smaller radius, right? If the V isn't big enough, then the R goes down because the net force side is dictating how much acceleration you actually have to work with. So we talked about this before, and I think we should address it again. This is a potential conservation of energy problem, but when the ball gets here, you need to have enough energy for the ball to not only make it just to that point, but to have a sufficient velocity to maintain centripetal motion. So it's not enough for the ball to just make it to the top. We'd already know that this condition must be fulfilled. Now, we've done this problem before. The ball is experiencing two forces, weight and normal force. And if we remember, we're going to make downwards positive because that's the direction of the acceleration. We'll set this equal to mv squared over r. I would like to make sure we have enough of that velocity. And that means probably knowing where along this part of the ramp to start the ball so it has enough energy to reach this point in the problem. Now, some things to consider: if we go high enough, then we'll just have the track pushing on it. We can always have more normal force. But our limiting condition is when the normal force gets so small it's no longer in contact with the marble. So we need this velocity to be greater than or at least equal to this condition. And cancel out our m's, and we'll get v squared has to be greater than or equal to g times r. Now, I've got a meter stick and we can take some measurements, but considering the time, I think we should take a look at the other part of the problem first. How do I make sure I have this much velocity when I make it to the top of the loop? Obviously, it is a ramp. I could do forces along the ramp, but the moment I make it to the circular part, that kind of goes away. So I think this is an energy problem. And if we assume there's no losses due to friction, I think we're going to start, say, the marble somewhere over here in hopes that it makes it to the top of the loop. I'm going to choose a reference level that is the bottom of the loop. I don't have to, mind you. I could say choose this as my reference level, which makes some sense, except that looking at the apparatus over there, it's going to be way easier for me to measure the height above my table than it would be to try and measure the height above the top of the loop. Does that make sense? So I'm going to choose the bottom of the loop as my reference level. When I do, I'll notice that this height right here, this is 2 times the radius of the loop. You guys see that? All right. And that clearly, this is just the radius. So if I go back to my concept of conservation of energy, I will have gravitational potential and kinetic when I'm here. And I'm going to release the ball with just gravitational potential. So I don't know how high this is, but I bet we can figure it out. Do you see the two states that I've kind of equated together? Does that make sense? There. You guys in the back, you guys see it okay? Well, I did take a moment already and found an expression for v squared. So we can put those together. mg times 2r plus 1/2 mgr. All right, just subbed in for v squared. Now both of these have mg and r together, so it's 2 plus 1/2. I think that's just going to be 5/2 mgr. Right? 2 plus 1/2 is 2.5. That's 5/2. And this equals mgh. So it seems to me I need to start the marble at a height of 5/2 times the radius. Yeah, see that okay? Now first, this problem involved understanding there was a limiting condition that had to be met. We decided that we needed to have enough energy so that this limiting condition could be met. That was dictated by a certain amount of kinetic energy necessary for the ball to have sufficient velocity to go through the loop. We then used conservation of energy to figure out where the ball needs to start based on how much energy the ball has to have to successfully make it through the loop.